Let's try a slightly more complicated example. Here we have a motion diagram, and we want to make a graph of position versus time. This one's a little more complicated because now my dots are not evenly spaced. So let's see what happens in this instance. So we're going to start again by making a position versus time graph. My x in meters on the y-axis, on horizontal axis. We'll have time in seconds. See, my total displacement is 9 meters, so I want to go up to 9 meters. And let's just break this into thirds for now. That's a 3, that's a 6. Okay. So at 0 seconds, t equals 0, starting off, I'm at 0 meters, so I start off right here. Let's give some time coordinates. 0, 1, 2, and 3 seconds. So we're starting off at the origin. And then 1 second later, we're at 1 meter. So 1 meter would be about here. So I haven't gone too far just yet. Then at 2 seconds, we're 4 meters away. So 4, 5, 6, we'll be right about here. 2 seconds. Where are we at? We had 4 meters at 2 seconds. Where are we at 3 seconds? Well, at 3 seconds, we're at 9 meters. A bit better. So now, all of a sudden, you can see, I can't just get a straight line for my plot. Now my position versus time graph is giving me something that has some curvature to it. So my displacement every second, my delta x gets bigger and bigger every second. So let's make some notes about this. Delta x increases over time. My displacement increases with each time interval. The displacement from 0 to 1 second is smaller than the displacement from 1 to 2 seconds. Similarly, if I look at the slope of my graph, here's my slope initially, then I have this slope, then I have this slope. You can see that slope is getting steeper and steeper. So we can see that my slope increases. Every second, my slope is getting steeper and steeper. If my slope is getting steeper and steeper, that means, let me just get myself a little more room here. My slope is getting steeper and steeper. That means my velocity is also increasing. So I am not moving at a constant speed. I am going faster and faster and faster. Henceforth, we could say that we are speeding up as my velocity is changing. So when you are speeding up or slowing down, physicists have a word for that. We say that you are accelerating. So let's define acceleration. Acceleration, which we will give the symbol a to, is going to be delta v over delta t, which is the change in velocity over the change in time. We'll put a big box around this, since this is an important definition that you're going to want to write down. acceleration is the change in velocity over the change in time. Now, that seems pretty straightforward, but it's actually pretty counterintuitive if you think about what the sign of the acceleration is. And it has to deal with how we talk about motion in everyday terms versus how we talk about motion as physicists. So, a normal person, if they're talking about acceleration, will say that an object is accelerating or decelerating. So we would say that accelerating would mean that you're speeding up. However, if you were decelerating, a normal person would say that you are slowing down. Accelerating, speeding up, decelerating, slowing down. That's how we speak in normal everyday life. Now that leads to a little bit of confusion, because you would think that accelerating would mean speeding up, which would be positive. Right? You speed up, you get a bigger velocity, therefore you have a positive acceleration. If you're decelerating, you're slowing down, you have less speed, therefore your acceleration should be negative. That's not necessarily the case. So it is wrong, I'll put this in big letters. It is wrong to say positive accelerations, accelerations greater than 0, mean that you're accelerating. This is wrong. Furthermore, it's wrong to say that a negative acceleration, an acceleration less than 0, means that you're decelerating. Acceleration is fundamentally just a different quantity than that. The way to see this is to go back to our definition. You can tell this is a definition because I have 3 equal signs. That means it's defined to be true. Now, if we keep that definition, we can see why it does not mean that decelerating necessarily means that you are, if you're decelerating, it does not necessarily mean that you have a negative acceleration. Let's do a counterexample to that. Let's say here's you. You're running to the left. Again, remember we defined the right to be positive by convention. Here's you. And at t equals 0 seconds, so initially you have a velocity. I'll call that your initial velocity, vi, is 3 meters per second. And then 2 seconds later, you're still moving to the left, but you have accelerated a certain amount. So now you're going faster. So your final velocity, let's make that 11 meters per second. Now there's an inherent problem with what I've described here. We're moving to the left. You're accelerating to the left, so you're moving faster and faster to the left. Well, if I look at that, well, if I'm moving to the left, my velocity can't be positive. To the right is positive. My velocity has to be negative. That's an easy fix. Similarly, my final velocity also has to be negative. If we're talking about velocity, I need to take into account the sign of the velocity. Well, now let's plug into my acceleration formula. Acceleration is my final velocity minus my initial, or delta v over delta t, which is, in this case, again, just final velocity over the initial, t final minus t initial. But that would be my final velocity, which is a negative 11 meters per second, minus negative 3 meters per second, divided by delta t, which is 2 seconds, minus 0 seconds. Okay. So that'll be negative 11 minus 3, so that's negative 11 plus 3, that's negative 8 meters per second, divided by 2 seconds, gives me acceleration, an acceleration of negative 4 meters per second squared. Okay, so let's think what we did here. You're moving to the left, but you're speeding up. You are accelerating in everyday speak because you're speeding up. If we look and use our definition to calculate what the acceleration must be, even though you are accelerating, you get a negative value for the acceleration. So deceleration does not necessarily mean that you get a negative value. Acceleration does not mean that you get a positive value. So what does the sign of the acceleration mean if positive is not accelerating and negative is not necessarily decelerating? Well, what it means can be determined just by looking at my definition. So we're looking at delta V. Is delta V positive or negative? So it could be that delta V is positive if I start at a low positive number. So let's say I'm going 1 meter per second. And then all of a sudden, I'm going 10 meters per second. I've gone from 1 to 10, that's a positive change, which would mean I would have a positive acceleration. It would also mean that I'm speeding up because I'm going faster than I was before. However, let's say I started with a negative velocity. So let's say I'm going negative 10 meters per second. I'm going in the negative direction really, really fast. However, let's say I'm slowing up in the negative direction. So I go from negative 10 meters per second to negative 1 meter per second. Well, I've slowed down, so I'm decelerating, but my acceleration is positive because negative 10 my negative 10 meters per second became negative 1 meter per second. So I have become closer to the positive end of the spectrum. That's what the sign of acceleration means. If I want to get a negative acceleration, I have to move, my velocity has to become more negative. So there's two ways for that to happen. I could be running really, really fast in the positive direction to the right, and then I could slow down so that my acceleration, let's say I was going 100 meters per second that way, and then I slowed down to 10 meters per second going that way. Well, 100 going down to 10 is a negative change. It's getting smaller. So I would have a negative acceleration there. I'd be slowing down. You could say I'm decelerating. However, if I were going in the negative direction, and I started off really slow, going only 1 meter per second in the negative direction, then all of a sudden I speed up. I'm going 100 meters per second in the negative direction. I've gone from a small number to a larger negative number. That's more negative. That would be a negative acceleration, even though I am speeding up. And you would say that you're accelerating. So the sign of acceleration has to deal with how is your velocity changing, not whether you're speeding up or slowing down. So let's see why acceleration and deceleration do not get positive and negative signs, respectively. Let's take a quick example. Suppose at t equals 0 seconds, you're traveling at negative 3 meters per second. And at t equals 1 second, so 1 second later, you've slowed down, now you're only going at 1 meter per second. Now, in normal person speak, you're slowing down, you would say you're decelerating. Let's see what happens to my acceleration using my physics definition of acceleration, using my mathematical definition. Here we go. So acceleration is change in velocity over change in time. Change in velocity is the final minus the initial velocity, still over the change in time, which would be my final velocity is negative 1 meter per second, excuse me. Negative 1 meter per second. My initial velocity is negative 3 meters per second, divided by delta t. Delta t here was just 1 second. So it's negative 1 minus 3. That gives me a positive 2 divided by 1 is still positive 2 meters per second. Okay, So even though I am slowing down, my definition of acceleration tells me that I have a positive acceleration. So positive and negative accelerations don't have to do with speeding up or slowing down. What do they have to do? Well, by my definition, they have to do with the change in velocity. So if my velocity is becoming more positive, I'm going to get a positive acceleration. Here, let's see what happened. I had a negative 3 meters per second velocity initially. Then that switched to a negative 1 meter per second velocity. So I went from negative 3 to negative 1. Both of those are negative numbers, but the change was more positive. We went up by 2. From negative 3 to negative 1, you have to add 2. You're getting a bigger number. So my change in velocity there was positive, which means my acceleration was going to be positive. So it doesn't have to deal with whether you're speeding up or slowing down. It just has to deal with the change in the velocity. Are you changing to a more positive velocity or a more negative velocity?
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the 2 of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
There's a somewhat apocryphal story about Galileo dropping different masses from the Leaning Tower of Pisa. So here we go. Here's my Leaning Tower of Pisa. Here's my Galileo. And what he found was that no matter what the masses were, they all hit the ground at the same time, provided they weren't so light as to be affected by air resistance. But if you drop a 10 kilogram mass and a 20 kilogram mass, they hit the ground at exactly the same time. So what we can say is that gravity causes all masses on Earth to accelerate at the same rate. I should say to accelerate down toward the Earth at the same rate. Gravity causes all masses on Earth to accelerate down at the same rate. Now there's an important assumption being made here, and that assumption is that friction is negligible. So gravity will pull masses down to the Earth at the same rate, provided friction is negligible. However, we know that there are certain cases where we can increase the air resistance, increase the air friction. For example, a parachute does this, which is why we can go parachuting and still be safe when we land. Also, if I take a feather and I drop it, there's a lot of air resistance on the feather that prevents it from falling down. Now, if we go up to outer space, if we go to the moon and try the same experiment, where there is very little atmosphere, we can see that even a feather and another solid object, take a feather and a bowling ball, and you drop them at the same rate, you'll see that they still fall at the same rate, provided that there is no air resistance. So at what rate does gravity pull objects down to the Earth? It turns out it pulls it at a constant acceleration. And I can write that acceleration, approximately constant. I can write that acceleration, which I am actually going to use the symbol g for the acceleration of gravity. It is approximately equal to 9.81 meters per second squared. So every second, gravity pulls you faster by 9.8 meters per second. So let's round that up to 10, just to make my math a little bit easier. So right initially when I let something go, right as soon as my fingers are taken off of the object, initially it's not moving. So the instant I let it go, it's still not moving because it hasn't had a chance to speed up yet. So initially, right when I let it go, it's moving at 0 meters per second. If I wait a second, again rounding g up to 10, if I wait a second, 1 second later it's traveling at 10 meters per second. A second after that, it'll be traveling at 20 meters per second. The second after that, it'll be 30 meters per second, then 40 meters per second. Every second, it goes about 10 meters per second faster down toward the ground. Now, by convention, we usually define up as the positive direction. So we'd say up is positive, down is negative. And since we're accelerating down, our speed is increasing in the negative direction. Sometimes you will see this written with a negative sign. So you want to make sure that the sign expresses the fact that the acceleration is down toward the Earth.